All right, ready to go here? I haven't posted the lecture in Canvas from Monday, so I will try to do the Monday and Wednesday one later this afternoon. How are you guys doing? 2 thumbs up in the back. That's good news. I like that. Are there questions or concerns or something I need to know? Yeah? Okay. We are going to continue on our journey of finding roots. It's a big topic in numerical analysis, finding roots. And so far we've seen 2 methods. We saw the bisection method, and now we're nearly finished taking a look at fixed point iteration. And next, we're going to move on today to Newton's method. Okay, so we saw last time that if we had a function that we were doing, we wanted to find a root of, we could make an equivalent fixed point problem, and we can make several different functions that were equivalent fixed point problems. And some of them showed better performance than others in converging to the fixed point. So we got to just suss out exactly what that is and how to, yeah, that's a very technical term, how to decide which function to use. So here's the idea right there. We have a function g that's continuous. That's what that means there. Continuous on the interval AB, such that g of x is in the interval AB for all x in AB. Okay, so we have we sort of have a bound on the function, and then also, and this is the key point, that if the derivative of our function is less than k, and that k is between 0 and 1, then the fixed point will be unique, the fixed point iteration will converge, and we have this situation here that we can identify what the nth iterate is in terms of the original interval that we're looking at. Okay, so the key thing is when you are selecting which function to do the fixed point iteration on, you want the derivative to be bounded between 0 and 1. That's what allows it to converge. Okay, so let's just take a look at some of the ones we had. We were trying to find a root of this polynomial here, and we came up with several different functions for which we could do that. One was, I'm just going to call it g3 of x, right here, 2 of x, right here, and I think maybe I called it g4 of x. It doesn't matter. We just need to be able to talk about them. So all of these functions, doing fixed point iteration on any one of these functions is the equivalent of finding a root to this one here. Okay, so first major point is you can do it on when you're trying to get an equivalent fixed point problem, there is more than one for sure, and then they're not all equal. Some are definitely better than others. So let's just take a look, and this is of course where you're gonna, if you need to recall these skills, your differentiation skills. So we're going to have to know the product rule and quotient rule, the chain rule. So let's take the derivative here of g3. That's going to be minus 10 x cubed to the minus 1 to the minus 2 times the derivative of the inside 3x squared. Okay, so then we're going to, I'm going to pick an interval, and the interval I picked is 1.5 to 2.5 because you need an interval. So we talked earlier about maybe you're using the bisection method until you get into a certain interval, or maybe you know roughly where the 0 is. Whatever that is, you need to pick an interval, but that interval, and you need to look at what the maximum value of the derivative is on that interval, and that interval should contain the root. So let's just, for sake of computation here, say that we can find the maximum value of g prime of x on the interval 1.5, 2.5. Okay, this would be our closed interval method that you would use. Remember that you're finding the maximum value of this function. So if you're doing this by hand, you're trying to find the maximum value of that function right there. That means you have to find the critical points. We're using that closed interval method from calculus 1. You need to find the critical points, and you need to think about the endpoints. The critical points are when the derivative is 0 and or the derivative doesn't exist. Okay, but it's not the derivative of this function. I know this function, this is where I think some confusion comes in. This function is a derivative of something we're interested in. But when we're talking about finding the maximum of this function, we have to take the derivative of that function. Okay. Is that clear? Yes, no, maybe so. Yeah? Okay. So now I'm trying to find the maximum value of this function. I mean, you could just call it something else on this interval. So I'm not going to go through all of the details. So I've got here, let me just see if I got the number here. Let me make sure. Yep. That way, let's do this. Okay, I get that to be, so you should check with your calculus skills, you can do this. Okay, this is rather obviously not less than 1. Okay, so now let's take the next one. Let's take this guy here, g2 of x, and take its derivative. That is what? That is 1/4 x plus 10 to the minus 3/4. Okay, and now I'm gonna do the same thing, calculus 1 method, for I'll just ask both time also what is the maximum value. I'm gonna maximize g2 prime on the same interval. And I find that to be, that is definitely less than 1. Okay, now I'll just write out what the fourth one is. G4 prime of x, taking the derivative now of this guy here. You have to use the quotient rule there, minus x minus 20 over x squared x plus 10. Okay, so we take the derivative then, we maximize it. On the same interval, and we get 1.40. Okay, so based on this analysis, we would do the fixed point iteration with this function. Is less than 1 and bigger than 0 on that interval. That is the one that's going to converge. The speed of convergence depends on how small the derivative is. Yeah. Well, this is what is a little bit difficult, and that is a good question. So I don't know if we did it last time or not. I can't remember, but I'm looking at this function that we're trying to find the 0 of, and like let us just calculate out what is. Let's just call this thing f. F of 2. So f of 2 is 16 minus 14, which is 2. Actually, that is a fixed point. So that's what we want to find the 0 of, not what we want to find the fixed point of. But okay, did I do this right? Yeah, let's see, 2, 4, yeah, 16 minus 14. Yep. So this is not 0. So I am sort of in some sense taking a guess at where the 0 is, and then I'm just going on. I'm just looking at an interval close to that where I'm going to start. I'm going to start the fixed point iteration at 2. I made this decision somehow, right? And then I'm going to say I'm starting the fixed point iteration at 2, so close by to 2, hopefully containing the root. Like I could do this then as well. Like I could be using sort of the intermediate value theorem. What is f of 1? F of 1 is 1 minus 14, and that is minus 13. And f of 3, well, so I know the root, in fact, is between 1 and 2. So I'm using maybe a bisection method, or I'm using intermediate value theorem to come sort of close in an interval, and then in that interval, I'm going to check out what the derivative looks like, and then I'm going to pick the better function. It is true in case, in fact, I have a note here. This one here, this one here that I wrote this down. It's a true statement. This was on the interval, just like the other ones, 1.5, 2.5, like that. But it is also true that this one here, if I did on the interval 1.8 to 2.5, I would find out that it was 0.9793. So you may find if you were to use this guy here, depending on how your thing works, you might actually convert, right? How you're going to get at some point the focus too sweet, and you too off, and it's not, then you're good. So it's a little bit dependent. So you want to, but you definitely don't want one that looks like this. And if you're being more cautious, then you widen the interval and maximize the dividend on a larger interval. This whole business is about where to start and where to look at your function is well, it's the reason we're always going to have a number of iterations and stopping for when we don't see convergence. And I think reading the math documentation on this is instructive, because we'll do kind of the same thing. It's like, well, we do this, and then we start, and then we use bisection, and then we get close, and then we change the method. But if that stops converging, then we go back to the bisection, like this, to try to avoid these kind of issues. Okay. The point is here that when that fixed point iteration converges, it is linear, as is the bisection, and the constant is k. What is that constant for bisection? What was that? Remember? No, it wasn't 0 to 1. There's an actual number that the bisection, the lambda for bisection, is a half, right? Because we're putting the interval in half each time. So fixed point, it's still linear. That means that alpha is 1 and lambda is k. That's what this is telling you. And so, and bisection was alpha is 1 and lambda is a half. So if the derivative is approximately a half, you don't gain anything out of this method. If your derivative is very small, then that constant is more in your favor, and you're going to be going faster. That's what the statement is saying here. But it's still linear, so it's not this enormous big improvement. But it is an improvement if your derivative is less in absolute values than a half. Okay, let's just draw this out so we can see what's going on. Okay, here's that all important line y equals x. Now imagine here's my function here, g of x. That's the function I'm trying to find the fixed point of, which is clearly right here. Okay, and you'll notice, you can tell that the g prime of x is less than 1 because it's below the line y equals x. So it's got a slope of less than 1. And what happens, you take a guess, do not, come up here like that, you go across to the line y equals x, you come down, you get the value of p1. And you go up to your function, you get evaluate the function at p1, you come over to the line y of x, you come down here, and you get your line and then you go here, and you're getting closer, and here you're quite nicely. Okay, that is g of x, quite nice. Let's draw them a little bit closer. So that's the derivative less than 1. This derivative is still going to be less than 1. Here's our nice line y equals x. And we're going to make g of x still have a derivative less than 1, but not quite as nicely. Maybe there's g of x. There's g of x. We're still trying to find this fixed point. Just going to draw the same situation again. We take a guess. Not. We evaluate the function. We go over the line. We get our next value. We come down. We evaluate the function. We go over. We get the next value. I hope you see what's happening. Anyways, we get the next one. It's converging, right? It's still the derivative is still less than 1. But you can see that as the derivative gets closer to 1, like in this case here, it's taking many more steps to get close to that. Well, this is derivative, in this case, g prime of x is less than 1, but not by very much. Like 0.9, something like that. Okay, now let's look at the problem when the derivative is not less than 1. We have our y equals x line, and now we have some function with a fixed point. Our function looks like that, say, clearly in this case, g prime of x is greater than 1. Above the line y equals x. We take an initial guess. Then my line up here. We take an initial guess here, 2, 0. We're actually kind of close. And we go up like that. We hit the line, and we hit the function, and then we're like, okay, we need to go across to the line y equals x to get our next estimate. There it is, 1. And it's such a bad example that it's not. So now we would go up and evaluate the function, and we would go across to the line over here. Things are not looking good. The steeper that thing is, the faster that happens. Oh, this is not hard to detect, actually. If you're programming, you take an initial guess, and then you complete your next one, and then you have more distance here, and then you're like, okay, because this problem, fixed point iteration relies on you being able to compute the derivative. And that is, well, either a symbolic calculation, or as we're going to come to, do a numeric derivative. We're going to learn how to do numeric differentiation. So you do that, but you do have to require some extra calculations to set up and start going. That is fixed point iteration. It matters which of the functions you pick. So a typical way for me to ask you about this is to say, right now, fixed point problem. Okay, let's take a look at the next method. You guys have seen this one before. That will be Newton's method. We are going to derive Newton's method as opposed to just presenting it as a fait accompli. And that will allow us actually to talk about this method actually is quadratically converging under certain circumstances, which is very nice because that's much faster. Okay, so we're going to derive Newton's method using the Taylor theorem. This here, just like before, this means C2 continuous means that the function is continuous and the first and second derivatives are continuous. It has some root. We're going to call that P. We're going to take a guess at what that root is in some interval, maybe. And we're going to have at least to start here, that the derivative at our initial guess cannot be 0. And we're hoping that we're fairly close to where we want to go. Okay, so what we're doing then is a Taylor series expansion uh, of the function at the root. So we have here, this is a Taylor series centered around P naught. And so here we have f of P naught. So this is the Taylor series here. So all we do is say that if P minus P naught is small, then this thing here and all the higher order ones are small, and we're just going to toss them out because this thing, if this number is small and particularly less than 1, then when we square it, it'll be even smaller. And then when we cube it, it's even smaller. So we're just going to toss out all this stuff here. And then we're just going to simply say at our root, f of p, it's 0. That's why this becomes 0 right here. And then that is approximately going to be f at our guess plus p minus our guess times f prime at our guess. And we solve for p. That is what we want to know. We do that and we get this, Newton's method. You've seen this formula before. Okay, so now what we then the next thing that we do is we say, okay, we can make an approximation in this manner, and then we'll turn it into an iterative thing by taking our first output and making that our new input, and we try to get closer and closer. So what we're doing is we have p, we have p is being approximated that way, and then instead of doing, we say, okay, actually let's take and just make the first approximation, that thing there. Calculate the first approximation. So we take a guess, that's P naught, and then we compute our first approximation from that. And then after that, we take that new hopefully improved approximation, and we make the same calculation like that. And we just keep going and going and going until we find the root. Method. What's the other two methods? Our n plus first one depends on our. You can see clearly here why the derivative cannot be 0 at any of the ones that we picked. It's important when we drove the method, we said the derivative can't be 0 at our initial guess, and it can't actually be 0 at all. If that happens, then you have to stop because you cannot continue with the calculation. So what do we end up with here? We end up with a sequence of numbers, Pn. P naught, P1, P2, that range from n going from 0 to infinity. And we hope what we get is obtained. And we hope that the sequence converges to P. That's the rate. That's it. Anybody got a question about the method itself? Let's just take a look at how it looks graphically. Just a bit. You take an initial guess. Look at this here. You take an initial guess right here, P naught. You then evaluate your function at P naught. So you're at that point there, P naught f of P naught. Then you take the derivative, and that gives you that tangent line right here. So you take the derivative at P naught, and then what's happening is you then use that tangent line, and you go until it intersects the x-axis, and you're like, oh, that's probably my root there. And then in your next iteration, you evaluate the function at that point, and then find the tangent line at that point, and then you find where does the tangent line intersect the x-axis, and then that's your next best guess of where it is, and then you keep going like that, and then there will be a tangent line here, and you can see that actually in fairly short order, in this short case, that tangent line comes across the x-axis where the root of draw this diagram out and see why this method is working. Now, and you can also probably see, in fact, when this doesn't work by drawing yourself a couple of functions and taking a look at that. Okay, we can interpret this as a type of fixed point iteration, and we're going to do that because that allows us to see what type of convergence we're getting. Let's recall f of x, that is the root finding problem, and that's equivalent operation on p of x equal to f of x plus x. Okay. Let's just remind ourselves of why that is. Let's look at this function here, which I'm going to form fixed point operation on. And I'm trying to find where does g of p equal to p, and that is when, well, that is equivalent of saying g of p minus p is equal to 0. And f of x is equal to p of x minus x. So here, f of p is equal to g of p minus p. That's 0. There. So that's just showing you that that is really the equivalent to okay. Using Newton's method, let's see. We're thinking that we have p of n. We're finding the nth estimate of our root using some function of our n minus first estimate of the root. And what is our function in this case? That would be if g of x was this guy here, x minus f of x over x prime of x. So I'm just taking that right-hand side of the Newton's method thing, all that function here. And then what we're doing is fixing on that function. Okay. Then we recall we just saw a demonstration of this fixed point iteration. Converges faster when p of x is, what I'm going to say, locally flat, really, really small. Let's figure out what g prime of x is when we're thinking of this in terms of fixed point iteration. We have g of x is equal to this. We're going to calculate out g prime of x. That looks like this. 1 minus, I am taking the first derivative of this guy with respect to x. F prime of x. Bottom times derivative of top minus top times derivative of bottom of the bottom square. So then I do a little bit of algebra. I see the form of x looks like this. F of x, f double prime of x divided by prime of x. Okay. When we're close to the root, we're called p. Now we're saying we're close to the root p. Then prime of x is approximately equal to p prime of p. X is close to the root, that means x minus p. Time at p is approximately 0 because f of p is 0. Right? But this guy's sitting right there. So Newton's method actually should converge fast. So it's a quadratic convergence. Actually wrong. Okay. There's some practical things here. We haven't quite got this finished yet. Let's just talk about some of these practical things that we've had to do. Practical issues. We require a derivative. Okay. So this problem, requiring the derivative, can be somewhat solved, and that would be the solution here is typically use the secant method. Coming soon. And that's where you approximate the tangent line by the secant line. Probably maybe thinking back to first year calculus, we first got the average rate of change, and that was the secant line, and then we went to the instantaneous rate of change, and that's when things went from being the slope of the line between 2 points to the slope of the line at a point. Now we're just going to go back and go, hey, if we could just approximate the derivative using the tangent line using the secant line. Okay, what are the practical things? It requires that the derivative at every single one of the iterations of what we think the root might be non-zero. Division by 0 being one of those things we still don't like. All right. Most effective. Draw picture. Most effective if the derivative f prime is bounded away from 0. Here's the root. Let's just draw a little picture here. There's a function like this. It has a root. If I make my initial guess right here, then I will take the tangent line there. It doesn't even cross the x-axis. So now I can't even get to P1. So that if you have a very small or 0 derivative near the root, then it's not going to, things will not be going well. It's sort of in concert to that, it requires a good initial guess. And this is actually something that's come up several times in all of our methods. Like, how do I choose the initial starting point? Like that. But upside of course, is that you could start and say I'm gonna evaluate the function as 1,000 points and see which ones are maybe are close to zero. Or see where I can find it. Not that kind of computational power. Of course, you want to be as efficient as possible, but in terms of finding an initial value, you do have this advantage of just being able to try a bunch of things which you can't do effectively by hand. I mean, this, as I'm learning from my daughter who's got a job in cybersecurity, I'm learning that some portion of hacking into websites is just having that computing power to try a known amount of things. For example, known passwords. You have like the top 10,000 passwords that people are kind of predictable. The top 10 passwords, there are some phrases which are quite rude and commonly used for passwords. Okay, probably some of you are going, oh no, that's my password. Okay. You have this list of 10,000 passwords, you try them all against all the usernames. And oftentimes you'll get a hit, right? You then try them all with one appended to it. Try them all with one. Try them all with one extra. You know, like that kind of thing. Actually, even though that wouldn't be practical by hand in the same way, it's surprising how often you can then get somebody's password just by doing that. So think about that when you want to use whatever phrase that is. Pertaining to, say, human reproduction, those kind of passwords, it is not uncommon for, there's databases that consist list of passwords ordered by how often they're used. Okay, the same thing here. You've got a computer, you can try a whole bunch of initial guesses, not like doing it by hand. Okay, you do want to have a good initial guess. What else? Stopping criteria. You need some way of stopping. And so common ways are the distance between subsequent calculations. So you take that or go below a certain tolerance. So you're like, okay, I got P0, P1, P2, and now it's not changing that very much. I should stop. The other possibility is to do it in a relative manner, like this. Set in advance. So you stop. And also for the Newton's method, you need to have a maximum iteration. So you must use a maximum iteration stopping thing. Don't just keep trying and trying, getting nowhere. Method can diverge. I'll just draw yet another picture to show this. Here's a function like that. It has a root at 0. And you come along, and even if you take, in fact, let's even I've drawn this well enough. Let's even be close. Let's realize that we're actually came close on our first guess. Take the tangent line there, and we get P1 right here, and then we take the tangent line here. Get P2 here. Take the tangent line here. Get P3 here. Things are not looking good for us, right? And still fall out. So you have to stop once you notice that things are not going well. Okay. Well, it's true that you can be close and still diverge. If you are super close, you will converge. Okay, so I mean, at some point heading into the 0, the line is the the curve will be such that you will be able to get close enough. Unfortunately, that close enough is not predictable in advance. So I'm just going to refer you to the here. Take a look at theorem 2.6 on page 7 of the text. So this is basically if you are close enough, and that is sort of defined, close enough, you will converge. And so that means that your initial guess is within some delta of the actual root. But delta is usually unknown. And it's difficult, so it's difficult to guarantee, and it's difficult to guarantee convergence in advance. What we're watching for with this method. Okay. The good news is that in practice, what happens, one of two things will happen. Converges fast. That's good news. Or it's obvious it's divergent quickly. Or ditch it and move to something else. Okay. All right, so let's now see if we can figure out what is the order of convergence. We're thinking of it as a fixed point iteration, like that, where we have g of x being the Newton formula. We've already calculated the derivative. That looks like this. Okay. Right. G of p is p. G prime of p is, somebody sees that, does somebody see that right away? What is g prime at the root? Anybody? Well, this is how you calculate g prime. Substituting in t. 0, thank you, right? That's because f of p is 0. That's what we're trying to find. This guy right here is sitting there at 0. So that is 0. Okay. Our n plus first estimate is g of pn. Of n plus 1 minus p is equal to g of pn minus p. I'm just subtracting p from both sides there. Of n plus 1 minus p is g of pn. And what is p? Well, p is g of p. Fixed point iteration, g of p is p. Okay. Moving stuff around here so that I can tell you what convergence is. G of pn is g of p plus pn minus p times g prime of p. What is this? Plus pn minus p squared over 2 times p double prime of p plus, what is that? That's the Taylor series. Okay. on sum of p, this guy right here is 0. That term is 1. Now I have here g of pn, and I'm gonna I have this statement right here. You'll see that this is g of pn minus g of p. I'm going to subtract from this statement here. I'm going to subtract g of p from both sides. Okay. I have g of pn here. I'm going to subtract g of p from this side. That gives me g of pn minus g of p. And I'm going to subtract g of p from the right-hand side. That guy's going to go away. And then I'm here, pn minus squared over 2 p double prime of p dot dot dot. And further, this right here, because of this statement right here, this is p of n plus 1 minus p. Getting to where I'm trying to get that order of convergence thing happening. So look where I'm at. I've been fiddling around here, and I've shown that this thing is equal to this thing here. Now I'm going to just make an approximation by losing all of these terms here. And I can then write this as p of n plus 1 minus p is approximately p n minus p squared over 2 times p double prime of p. Then I'm going to rewrite that this way. Pn plus 1 minus p over pn minus p squared, approximately 1/2 p double prime p. There. How exciting is that? Quadratically converging. I did all that work just to make sure that there was a 2 here. So alpha is 2, and lambda is this guy here, 1/2 times the absolute value of the second derivative at the root. The important point is that that's no longer a 1. We're going to see a picture of this. No longer a 1. That means this thing is much faster. That exponent is bigger. The code I highly advise you to run the code and see this on your own so that it makes you happy. But here I've got some pictures. I'll draw some pictures here. These files are in Canvas. You can take a look at them. But imagine we're trying to compute the log of 5. They were trying to compute the log of 5. We want to set up a root finding problem to find the log of 5. So we find this thing here. Find the 0 of that thing right there. Okay, let me just draw you the little picture that you'll be able to manufacture for yourself running the code. This is the log of the error, and this is the number of iterations. So I take a guess, and then I know what the answer here is, so I can calculate the error. And if I do bisection method, I get something that looks like that. Bisection, green is bisection. And if I use Newton's method, it's a little bit slower at the outset, and then it goes like that. The waterfall effect. So you get, well, you sometimes start with the bisection method for a little bit, and then you're like, okay, I'm getting closer, and then you move to Newton's method, and it converts much more quickly. Not linear. So you see the bisection method, that is alpha is 1, and that is a linear convergence, and then this one is the Newton, and it's not a straight line, and it's quadratic convergence. It's a nice method. has some drawbacks, but it's fast when you're close. Okay, we are out of time for today. We're going to turn on Friday. We will have a quiz, and then we're going to finish with this and potentially start the polynomial interpolation, which is our next topic. Thank you, guys. See you on Friday.